we are going to talk about finding the area of a few shapes here. And if you look at the example that we have, there's this shape we're going to call S, and you haven't seen anything like it before. When you were in geometry, it's not as though you ever found the area of something like this. So as far as geometry is concerned, you're kind of out of luck with something like this. But here's what we're going to do. What we're going to do is slice this into little bitty slices, and they're going to almost be rectangles. So if you look at the slices, here, okay, so this is what a real slice would be. And if our slices is skinny enough, they are going to look like a rectangle. And each rectangle is going to have a width of, well, let's just call it delta x. It's teeny tiny. And the height of each rectangle, well, the top is always going to be a motion in this direction, right? So whenever we're moving in that direction, I think of that as a big change in y. So my y value up here is always defined by f of x, and my y value down here is always defined by g of x. So for every single rectangle, our height is going to be f of x minus g of x, and our width is going to be delta x. And we realize that we're going to have different y values here, but they're all defined by this. So we could even say we're taking the sum of all of our f of x of whatever minus g of x of whatever times delta x. And if we take the limit as delta x goes to 0, you know that we're going to have a Riemann sum. And it's going to look like this. It's going to be f of x minus g of x times dx, right, delta x, from A to B. So if we have something like this, so in the previous example, g of x was kind of dipping under the x-axis. Over here, they're both positive. So still, I'm going to slice this up, this region, and notice the height of my rectangle is still going to be the top minus the bottom, and the thickness is going to be delta x. What about if g of x and f of x are both negative? So suppose we had something like this. Here's our x-axis. Let's suppose this is f of x, and g of x might be somewhere down here, right? And I'm still going to take, this is still a big change in y for my height. So I'm still going to take f of x minus g of x. And it looks a little bit funny, like f of x over here might be, let's suppose x is 4, y is, I don't know, negative 3. And over here, x is still 4, but y is, say, negative 6. If we do f of x minus g of x, which is a negative 6, that still gives us a positive height for the rectangle. So it's always going to work to do top minus bottom. Okay, so then for something like this, here's what we're going to do. We're looking for the area of this thing. Here's a sample rectangle, but if I sum up all of those rectangles, we're taking all those rectangles between x is equal to 0 and x is equal to 1. Top function is e to the x, bottom function is x, times the thickness is going to give us, well, just e to the x minus 1/2 x squared. And if we plug in 1, that's going to give us e to the 1 minus 1/2. And if we plug in 0, that's going to give us e to the 0, which is 1 minus 0. So our total area is just going to be e to the 1 minus 3/2. And this gets a little bit trickier. First, you're not given a diagram. Find the area of the region bounded by these two curves. Well, let's give ourselves a diagram. We know what y is equal to x squared looks like. We know that's a parabola opening up. We knew 2x minus x squared is a parabola opening down, and we know that our x-intercepts are at 2 and at 0. So we're going to have a region bounded between these right here. And we need to know our limits of integration. We know we're going to do top minus bottom, and clearly this is the top. But for our limits of integration, let's set these equal to each other and see where they intersect. So x squared is equal to 2x minus x squared. Still quadratic, so let's set it equal to 0. So 2x squared minus 2x is equal to 0. Let's factor out a 2x and that leaves us x minus 1 equals 0. So our points of intersection are at 0 and at 1, so we'll just set up our limits of integration. 0 to 1, top is 2x minus x squared, bottom is x squared dx. And then you can do this, 2x minus 2x squared dx, 0 to 1, so that's going to give us x squared minus 2/3 x to the third between 0 and 1. If we plug in a 1, we get 1 minus 2/3. If we plug in a 0, we just get 0 for both of them. So the area between those two functions is just 1/3. And there's a graph of what we were doing with the sample rectangle drawn.